Okay, this might be the last video in Chapter 7 and 8, the Intro to Quantum Mechanics. I left off by kind of showing how the periodic table came to its shape, matching the theory from orbitals, which fell out of the solution to Schrödinger's equation, the wave equation. And it really is, it kind of finally allows a lot of these chemical elements, and in fact even chemical properties or atomic properties, to make some sense. And so the model, the electron model that we have, again, it's this model where electron is kind of a wave. It follows a certain probability distribution and therefore kind of gives the atom some shape. And the shape of an atom is largely the shape of its electron cloud, meaning essentially where the electron happens to be. And in fact, one of the chemical properties that we'll look at that there's trends for is the atomic size. And atomic size is really the size of the atom, not just the nucleus, but the size of the electron cloud itself. Essentially, the rough size of this electron distribution shape that we've been talking about as it matches up with orbitals. Okay. A couple of things I want to point you to. First of all, when I zipped through in the last video, I zipped through filling up the 10 elements between scandium and zinc, and I just sort of arbitrarily filled one at a time in the set of 3Ds. It turns out that's not exactly correct. There's a couple of anomalies. It's largely correct. In fact, the very simple-minded formula I was using to fill up these orbitals is pretty close to correct. There are some exceptions, especially when we get into the Ds, like when we encounter 3D. And then the same sort of exceptions occur when we get into the Fs, the 4, and starting at 4F. Okay, turn to table 8.4. And 8.4 has an interesting depiction, I don't know if I can get it there, that shows, starting at potassium, which is atomic number 19, how the orbitals fill all the way to krypton. And I'm going to just point out a couple of exceptions to you. So they all kind of fill using the exact same sort of strategy that I was using, which is whenever you got another electron, you just put it in the lowest orbital that's available. One exception, the first exception you see to that kind of easy model is chromium. If you look at chromium, you'd expect chromium at 24 would look just like vanadium, but instead of it having 3 electrons in the 3D orbitals, it would have a 4th. So you'd see a square that has a 4th electron going up, and it was still one empty square next to it. Turns out chromium, from an energy standpoint, it's actually better from an energy standpoint if chromium, instead of leaving an empty orbital at the 3D level, it instead actually converts one of the 4s's to fill that 5th spot. And so what you end up with is, and it looks pretty strange, but what you end up with is a case that when you get to atomic number 24, the 4s orbital isn't filled. It's only half filled. And instead, kind of as a balancing act, it's kind of a pro and con thing. Well, it's not filled, which makes it a little less stable, but we actually were able to partially fill all 5 of the 3D orbitals. And it turns out from an energy standpoint, this produces a more stable atom. And we kind of see this a lot, is that filling an orbital, or even half filling an orbital like we're seeing here, is a more stable arrangement. Now when you think about this, going back to our geometry that we did, this kind of makes sense, because half filling a 3D orbital means essentially using all 5 of those shapes when L equals 3. Remember when L equals 2. When L equals 2, there were 5 shapes. And it kind of makes sense to at least half fill all 5 of them to produce a good symmetry around the nucleus. An easier way to think about this, if you think about the p state, again, the p orbitals have an x, a y, and a z, that when you when we put just 2 electrons there, you have one in the x and one in the y, but nothing in the z. And so it's not symmetric anymore. It's kind of, it's wobbly. It's like a table with 2 legs. But then when you add in the z shape, now all of a sudden, even though they're not filled, they're only half filled, it's much more stable because it's symmetric around the nucleus. The exact same thing happens, but even in a bigger way, once you get into these higher shapes like D and F. And so in the case of chromium, it's way more stable to half fill all Ds and leave the 4s half filled also. Okay? Now, when we get to manganese, manganese adds one more electron. So there we add it back to the s, because there manganese can fill the 4s, but then still leave the other 5 orbitals half filled, and that's stable. So manganese is not really a departure. In fact, manganese is kind of what you'd expect to have happened, ignoring chromium. Same thing for iron. Iron just adds an electron as you'd expect. Cobalt as you expect. Nickel as you'd expect, just adding and filling the D. Then you get your next anomaly at copper. Copper has the exact same sort of effect as chromium, which is instead of leaving the orbital like almost filled, the D orbital, the 3D orbital that is, it completely fills it at the expense of one of the electrons from 4s. So copper and chromium are kind of analogous if you look at them. Chromium borrowed an electron from 4s to half fill 3D, and copper borrows an electron from 4s to fill the 3D. And finally we get to zinc. Zinc is nice and stable because now you have the S and the D all completely filled. Okay. So I want to point out that picture. The other thing I wanted to point out is, and remember I was in this crazy little depiction of the fact that 3D is higher than 4S and all that jazz. This is covered in a couple of different drawings that are actually pretty good on this side here. So look at figure 8.12 and figure 8.13, and that kind of shows you from an energy standpoint, here's the order of the orbitals. And this is essentially the same order that the periodic table follows. Okay. All right, now I want to turn my attention to, all right, so what do we do now? This is all neat, and it's great that it matches up to theory and all, but what sort of trends can we even see in the elements when shaped in this fashion? Okay, well the book in chapter 8 covers 3 trends that let's talk a little bit about. I think the text does a really good job, and I recommend you reading this text. But the 3 properties that the text calls out, where there are trends that we see along the periodic table, one of them, the first one is atomic. I'll list all 3: atomic size, and then there's ionization energy and electron affinity. Okay, and I'll discuss all 3. But the first one's atomic size. So there are indeed trends in terms of the elements, and there's a great figure. Figure .8815 kind of shows, at least for most of the elements, to go all the way down to n equals 6. It shows the relative atomic size, and it shows it by a shape of a little circle. Okay. Generally speaking, what this shows is that as n gets bigger, meaning as you go down the periodic table, the atoms get bigger. That makes total sense, right? Because in fact, the n number itself is kind of the size, is a size kind of thing. So it makes sense that as you go down a column, as n gets bigger, the atom gets bigger. Makes total sense. Okay. The other trend you can see, though, is that as you go across the periodic table, on any given row, the atoms get smaller. The reason why that is, and the text covers it pretty well, is that as you go across the table, you're adding in, and you're always adding in an electron as you go, but you're also adding in a proton. So as you go across the row, the nucleus actually gets more positive. And it turns out as you go across a row, the nucleus getting stronger actually more affects the shape of the atom more than the fact that you're adding another electron. So as you go across the table, the atoms actually get smaller. So those are the kind of the 2 key trends. Now there's some interesting anomalies, and the one in particular is gallium, and I'd love to talk to you about that one. I'm not going to spend time on the video, but gallium is kind of an odd one, and there's a reason why, and it's covered in the text. Okay, the second trend I want to cover is ionization energy. What ionization energy is essentially the energy it takes to expel an electron from the atom. Okay, so I'm going to erase now our picture. So, for example, sodium results in sodium plus an electron. Okay, and this will always have a delta H greater than 0. It takes energy to expel an electron from an atom. Okay, now what you'll see, and by the way, this is called the first ionization energy of sodium. The second ionization energy of sodium, or for that matter anything else, is to take a sodium ion and then have that turn into a sodium 2 plus and another electron. Okay, so the first one's called the first ionization energy And the second one would be called the second, I guess it's called ion 2 and ion 1 or something like that, whatever the depiction is. Okay? And what you see is that the energy it takes to remove the second electron is always higher than what it took to release to expel the first one. Okay? And that's mostly because at this point the sodium ion, it's now a cation, so the nucleus is even more positive than it was before, and so it's even harder to electrostatically remove that second electron. Okay. Now, the trends here, boy, how am I doing on time? The trends for ionization energy is that basically the ionization energies are always lowest actually for 1A, and I think that they become higher as you go across the chart. Also, I believe the ionization energies as you go down, as n gets higher, the ionization energies become less. By the way, this is actually a concept that I wanted to talk about also, and I should have done it before I erased all this, is that the electrons of interest, chemically, are always the electrons that we've added after the last noble gas. So for example, when we talk about sodium, sodium is basically the same as neon plus 1. And so what we say is that sodium has one valence electron. Okay, and valence electrons, and in fact the word valence is really important. Valence really refers to like the outer shell of the atom. And so in this case, sodium is at the third level, so it's really completed its inner two shells. So there's only one electron in the outer shell. So that's called a valence electron, one valence electron. Okay. Now, reason why did I even mention that? For ionization energies, we're shoot, I'm out of time too. Well, I can't remember why I inserted that whole concept of valence. Shoot. I guess I'm going to end this and do one more video.